This video lecture contains a very brief introduction to solvation models used within computational chemistry. We will here consider two different solvation models, namely the explicit solvation models and also continuum solvation models. Starting here with the explicit solvation models, the way that we introduce the effects of a solvent in those cases is by keeping simply all the solvent molecules explicitly represented in our calculation. This of course gives us a very detailed information about the solvent, but of course it is also very expensive for computations. And this of course is due to the fact that by keeping all the solvent molecules explicitly in our calculation, we have a lot more electrons and nuclei to be considered in the calculation, which of course will lead to a very high cost of carrying out such a calculation. Another way of introducing the effect of a solvent is to rely on the continuum solvation models. And what we do here is that instead of having all the solvent molecules represented explicitly, we represent here the solvent as one continuous medium, a dielectric continuum. In this dielectric continuum, we create a cavity, and in this cavity we place the molecule which we are going to do calculations on, that is the molecule that we are going to introduce the effects of solvation on. Now the dielectric continuum models are very simple, and these are also very inexpensive to use within calculations. However, they are of course less accurate as compared to the explicit solvation models, due to the fact, for example, that they ignore specific short-range effects. Now for the dielectric continuum models, a very important point here is how to construct and how to handle the cavity that we use in order to host the molecule. And here we can choose between some simple models, which for example treat the cavity as being a sphere, or we can go to some more refined models which makes use of molecular shaped cavities. In those more refined models, we can for example create the cavity by assigning to each nuclei here, for the case of water molecule here, a sphere, and then considering here this convolution of those three spheres here, and use this in order to define the cavity. In this case here, what we get by using van der Waals radii for these spheres here would be what we call the van der Waals surface. Now in some cases, the van der Waals surface here will give rise to some unphysical interactions, due to the fact that if we consider, for example, this region here, well, then this is actually so small in space that it is not possible for real solvent molecules to actually occupy this region here. So we can refine a bit here on this van der Waals surface here by introducing a solvent molecule in terms of such a solvent probe here, and then we can roll this solvent probe on the van der Waals surface, thereby creating this more smooth surface here, and also a surface which excludes part in space which actually is not accessible to the solvent. So this is what we call a solvent accessible surface, and these are probably the most used ways of creating the cavity in modern computations. Now when we are in a specific case to carry out such a calculation including solvation effects, then of course we need to choose the way that we should represent the solvent, that is either by using the continuum or the explicit formulation of the solvent model. And in many times this turns out to become a compromise between accuracy and cost. We can either introduce the solvent as a continuum, this would give us probably low accuracy but it will be very fast, or we can introduce the solvent explicitly, this will give us high accuracy but also a high cost. So the advice here would be generally to try to do the continuum models first, and then if you see some significant effects due to the continuum model, then you can think about going to the explicit solvent models in order to get even better results. So this is illustrated on the bottom of this slide here, where we can see that as we increase here from the continuum to the explicit solvation models, we also get a more realistic description, but at the expense of a higher computational cost.